As we start this discussion about AC circuits and phasors, I thought it might be useful to take a look ahead to machinery. Here is a prime mover. You could think of that as a 12-cylinder diesel engine, and that is driving a three-phase generator. If we were to model this generator, our model starts with an AC generator. We call this the internally generated voltage. It includes resistance. You could think of that as the resistance of the wires in the generator. And because the wires are wound in coils, they also present as inductors. The output terminals of the generator would be labeled A and B. Together, the resistor and inductor form the impedance of the generator. At this point, you might be thinking to yourself that that looks an awful lot like a Thevenin equivalent circuit. And you would be correct. That is indeed how we model and talk about the generator. Knowing that that's our target, let's back up a little bit and see how we get there. Some new terms. We want to talk about time domain and phasor domain. A time domain equation might look like this. Voltage as a function of time is equal to some maximum voltage cosine of omega t plus theta. Again, this is a voltage as a function of time. This is the peak voltage. Omega is the angular frequency, where omega is equal to 2 pi f. And this is the phase shift. And that will be given in degrees typically. As an example, V of t is equal to 170 cosine of 377 t plus 10 degrees. Knowing that omega is 377, we can solve for the frequency, which in this case would be 60 hertz. We can solve for the period, which is equal to 1 over the frequency. That's 1 over 60. So our period is equal to 60 inverse. And that should be about 16.7 milliseconds. Our time domain plot would look something like this, where this is maximum voltage, and this is negative Vm, hidden behind my head. The period from here to here would be 16.7 milliseconds. But we're not finished yet, because this particular waveform has a phase shift of 10 degrees, which means the waveform will actually occur slightly earlier in time. So that difference right there is about 10 degrees. Again, this is what our time domain representation looks like. Now we can come up here and we can convert from the time domain to the phasor domain. We'll start our discussion of phasor domain with a rule, and that rule is simply this. All voltages and current are in RMS form. We have a simple equation for this. The RMS voltage is equal to the maximum voltage over root 2. In this example, the maximum voltage is 170, so VRMS is equal to 170 over root 2. So that's 170 divided by square root of 2 should give us 120 volts. We do this because that is what your meter reads. To complete our conversion, we would say the RMS phasor is equal to 120 volts at a phase angle of 10 degrees. We can now plot this in the phasor domain. We have a real axis, imaginary axis. The phasor has a length of 120 and an angle of 10 degrees. We can put that into our calculator as 120 at a phase angle of 10 degrees, which tells us that this distance here is 21. We could call it J21. And this distance here is 119. So we can talk about our phasor as 120 volts at a phase angle of 10 degrees, which is our polar form, or we could use the rectangular form. We could say that this is 119 plus J21 volts. Both forms are correct. However, I would argue that this one is more useful because that is what your meter will read. As a sidebar, watch out for your voltage and time. For example, you may be given something that looks like this. The temptation is to say that the current is equal to 10 over root 2 amps at a phase angle of 20 degrees. That's close, but it's not correct. And the reason it's not correct is because this here is a sine term, and we need the cosine term. From trigonometry, remember that the sine of theta is equal to the cosine of that angle theta minus 90 degrees. And that's the conversion we're going to have to do in order to convert from sine to cosine. So in the time domain, I of t is equal to 10 cosine of 377t plus 20 minus 90 degrees. So your current is 10 cosine of 377t minus 70 degrees. And now you can do the phasor conversion. Current is equal to 10 over the square root of 2 amps at a phase angle of negative 70 degrees. And if you wanted to plot that in the phasor domain, here's your real, here's your imaginary, and this is 7.07 amps at an angle of negative 70 degrees. All right, moving on, let's talk about Ohm's law. In DC, we said that the voltage is a current multiplied by a resistance. In AC, this changes form, and we now talk about a voltage vector multiplied by a current vector by an impedance. Here's an example. We are given a voltage and a current, but they're both in the time domain. To make this problem easier, you want to get them both into the phasor domain as quickly as possible. The voltage is equal to 294 over the square root of 2 volts at a phase angle of 0 degrees. And the current is 28.3 over the square root of 2 amps at a phase angle of negative 20 degrees. 294 divided by the square root of 2. That gives us a voltage of 208, again at a phase angle of 0 degrees. Our current is 20 amps at a phase angle of negative 20 degrees. We can plot these vectors on the real imaginary plane. Here's the voltage vector, 208 volts at a phase angle of 0 degrees, and our current vector is at negative 20 degrees, and we said that was a length of 20 amps. As far as Ohm's law is concerned, we can calculate the impedance as a voltage divided by a current. In this case, the voltage is 208 at a phase angle of 0 degrees, and the current is 20 at a phase angle of negative 20. We can enter that directly into the calculator. Before we get started, make sure your calculator is set up correctly. Go to Setup. Make sure you're in complex mode. You'll know you are because you have this complex symbol right here. Now also make sure you're in degree mode, which is right here. So go Shift, Setup, and then 3. Again, you want it to be complex and have that D lit up. We can enter that into the calculator as 208 at a phase angle of 0 degrees divided by, we said 20 at a phase angle of negative 20, which gives us an impedance of 9.77 plus J 3.56. And that is in ohms. Jumping ahead, we would draw a schematic like this. We have 208 volts at a phase angle of 0 degrees. There is a resistance and there is an inductance, where the resistor is 9.77 ohms and the inductance is J 3.56 ohms. And finally, there is a current in this circuit of 20 amps at a phase angle of negative 20 degrees. To understand how we get here, I think we need to do a little bit of backtracking. And it starts with an acknowledgement that inductors and capacitors store energy. The work on a capacitor is 1/2 the capacitance voltage squared, and the amount of energy or work on the inductor is 1/2 the inductance by the current squared. Suppose we took a capacitor and connected it directly across an AC source. Source voltage, and then we'll let this be the current. In the time domain, we end up with a waveform that looks like this. We have the voltage, and then we have the current. You'll notice that this is a 90-degree phase shift. And that's not entirely unexpected when you consider that the current on a capacitor is the capacitance by the derivative of the voltage. This has some interesting implications. Here we have maximum voltage, no current. At this point we have no voltage but maximum current. Here we have another maximum voltage but no current. And here is no voltage but maximum current. Something I'd like to draw your attention to. Remember that power is a current by a voltage. On this graph, we have current and voltage, and we can calculate the power at any given instant in time. For example, here we have positive voltage, negative current. We would say the power is negative, right? When you put the signs together, you end up with a negative. In this piece here, we have negative voltage, negative current, so the power will have a positive sign. Moving on, we have negative voltage but positive current, which means we're back to negative power. And here we have power that is positive. If you put all this together, you could make a couple of statements. You could say that the energy is absorbed and then returned. You could also say that the energy is never consumed. If you wanted to state that in a different way, you would say that capacitors are not resistors. Remember, a resistor, if it was connected up to that power supply, would take in the electrical energy and convert it to heat, which is not recoverable. The capacitor takes the energy, for example, it will charge on the positive half cycle, and then it will return the energy back to the power supply and then charge up to the opposite polarity. So you have energy that's moving back and forth between the capacitor and the power supply, but it's never consumed. We have a word for this, and that word is imaginary power, otherwise known as reactive power. At this point, we're going to go over all of the rules that allow us to work these problems. So we start with Eli the Iceman. In an inductive circuit, voltage leads current. In a capacitive circuit, current leads voltage. We can think about this in the phasor domain. Here we have the real axis, the imaginary axis. We'll let this be our voltage. A capacitive circuit would have a current that leads. This would be current on the capacitor. And you remember that these vectors are rotating in this direction. So if you were a stationary observer right here, you would watch these things go by you in a counterclockwise direction. You would see current first, followed by the voltage. In the inductive circuit, you would have a current that lags. So this is inductive current. So again, as the stationary observer looking here, you would see the voltage vector go flying past you, and then a short time later, you would see the current vector flow past you. So voltage leads current in an inductive circuit. Some more things for your note card. We can talk about the reactance of an inductor. That's omega L, or 2 pi f L. Reactance is the opposition to the flow of current. So like resistors, it has units of ohms. The capacitive reactance is 1 over omega C, which is also equal to 1 over 2 pi f C. Another thing to remember is that this is a scalar. And you also knew that because there was no bar over that. We are most interested in the vector. So we want to talk about the impedance of the inductor, and that is JXL. Remember that this is the reactance, which is a scalar, and this is impedance with a direction of J, which means it's 90 degrees off the real axis. For the capacitor, the impedance of the capacitor is equal to negative JXC. On the real imaginary axis, it looks like this, where we have resistors on the real axis, we have capacitors in the negative direction, and we have inductors in the positive direction. Speaking of impedance, we can look at series and parallel connections. The rules are identical as they were for resistors. The total series impedance is the sum of the impedances, whereas 1 over the total impedance is equal to the inverse of the individual impedances. The voltage divider is still with us, so the voltage of interest is equal to the impedance of interest over the total series impedance by the source voltage. You can make sure that this is the series piece. The current divider still works. The current of interest is equal to the total impedance over the impedance of interest by the source. I'll make a note here that this total is for the parallel piece. You'll be glad to know that Thevenin still works, as do all the rules we used before to calculate a Thevenin voltage and now a Thevenin impedance. Something to keep in mind about this Thevenin impedance. Suppose you had some resistance, you had a fair amount of inductance, and you had a small amount of capacitance. When you were done, the Thevenin impedance of this circuit would be a resistor in series with an inductor. The reason you're left with an RL is that the capacitor and inductor are opposites of each other. So the capacitor could be subtracted from the inductive vector, which leaves you with this piece right here. Again, it'll appear as if it's a resistive inductive circuit. All right, we've covered quite a bit of material. Let's see if we can't nail this down with a few examples. Our opening move is to do a conversion and calculate the impedance of this inductor. So the inductive reactance is 2 pi by 60 by 0.25. If we run that through the calculator, that's 2 times pi times 60 times 0.25. So that's about 94.2 ohms. And we know the impedance of that is going to be J 94.2. So we can write that up here. This is J 94.2 ohms. Knowing that, we can solve for the current. So the current is equal to a voltage over an impedance. In this case, it's 120 over J 94.2. So 120 divided by 94.2 J, which gives us a current of negative J 1.27, which is fine, but I'm going to shift that into polar form. So go shift complex 3, which is, so that current is 1.27 amps at a phase angle of negative 90 degrees. If we were to plot that on the real imaginary axis, we would mention a voltage of 120 volts at a phase angle of 0 degrees. That's our source vector. And then we have this current here at 1.27 amps at a phase angle of negative 90 degrees. Because the voltage vector and current vector are at 90 degrees relative to each other, we could say that no work is done. The energy in the inductor will be stored, and then it will be returned. And you end up with this energy flowing back and forth between the inductor and the power source. Here's another example. To save some time, we'll use the value from our previous example. So this is J 94.2 ohms. The total impedance is the sum of the individual impedances. So this is 50 plus J 94.2. And we can stop right there and leave it as is. And move on to the parallel example. Here, 1 over the total impedance is 1 over 50 plus 1 over J 94.2. We enter that in the calculator like so. Use the parentheses. Use the parentheses, or you're going to get in trouble on this one. So parenthesis 50, invert, plus parenthesis 94.2 J, close the parenthesis, and then invert equals invert equals. It gives us a total impedance of 39 plus J21. We can stop right there with ohms. By the way, I forgot to mention that up here as well. That's ohms. What this tells us is this parallel circuit is the same as a series circuit with these values. In fact, if you were to look into these circuits, you can't tell this one from that one. They have identical impedances. Here's a series parallel example. We calculate the total impedance as J 94.2 plus 50 in parallel with negative J 60. And that looks kind of mean, but it's not so bad. What you do is you work this piece first and you lean very heavily on your calculator. So parenthesis 50, close, invert, plus parenthesis negative 60 J, parenthesis invert equals, invert that again. The impedance of the box is about 30 minus J25. Then we add the 94.2 J, which gives us a total impedance of about 30 plus J70. So our original circuit is functionally equivalent to a circuit that has a resistor and an inductor, where the resistor is about 30 ohms and the inductor is J70. While we're here, maybe we should work this backwards to find the actual value of that inductor. So this is J70, and we said that was the impedance of the inductor. The reactance of the inductor would simply be 70, and we know that the reactance of an inductor is 2 pi FL. We'll assume that our frequency is 60, so now we can find the inductance. So L is equal to 70 divided by 2 divided by pi divided by 60. So our inductance is about 190 millihenries. While we're here, I wanted to give you a quick caution. Watch out for your units. So in this particular case, 190 millihenries is the value that's physically stamped onto the inductor. But up here, we were using impedances, which are in ohms. What I'm trying to say is be careful. In order to calculate the total impedance, everything must have values of ohms. The trap people fall into is that they forget to do this initial conversion. They forget to take the value of the inductor and convert it into the impedance. You'll see that when people try to put 250 millihenries down here, and that does not give the right answer. So you got to be careful of that. Make sure it is in ohms before you get going. One last example and we'll call it a day. You'll recognize that as a Thevenin circuit. And the good news is that all of the rules we used before are still true. So your opening move in this particular case is to say, turn off the power supply. In this case, short this 120 volt source, which gives us a Thevenin impedance of 20 plus 200 in parallel with J100. Let's try that in the calculator again. So that's 200 inverse plus parenthesis 100J parenthesis equals equals. Okay, so that takes care of the box. And now we need to add 20. So the impedance of this is 60 plus J80 ohms. And now for the Thevenin voltage, you'll notice that this voltage here will be the same as that voltage because there's no current, because there's no load. You've removed the load when you did your Thevenin steps. Anyway, we can use a voltage divider here. So we can say that this is 200 over 200 plus J100. Again, all we've done is we've used a voltage divider for these two parts right here. And we multiply that by the source. Let's try that with a calculator. So 200 divided by parenthesis 200 plus 100J equals, and then you multiply that by 120. So it gives us 96 minus J48, which is true, but not very useful because that is not what our meter would read. So what we'll do is we'll shift that into polar form. And this is what the meter would tell us. We have 107 volts at a phase angle of negative 27 degrees. So when you put that all together, our Thevenin circuit looks like this. We have 107 volts at an angle of negative 27 degrees, with this being 60 ohms and this being J 80 ohms. Terminals A and B, and you looking in cannot tell this circuit apart from the original. They are identical. There's one thing I forgot to tell you. You could purchase a power analyzer. This instrument will show you the phasors in exactly the same way as we've shown them in this lecture. For example, there is your source voltage, and this vector here might be one of your current vectors. By the way, is that a capacitive or an inductive circuit? If we remember the vectors rotate in that direction, rotate counterclockwise, you would see voltage first. Again, you, the stationary observer, would see voltage first. Sometime later, you would see current, so that makes this an inductive circuit.